non-invasive brain stimulation. What the heck is that? Yeah, well, lucky for you, we have Ludovica Labruna here with us today to tell us all about it, including a new, exciting, revolutionary method of it called kTMP, which is being developed by her company, Magnetic Tides. Yes, we are entering a new age of brain and behavior change. Grab your electric surfboard and let's surf these brain waves together with Ludovica Labruna. So can you first explain to us, because a lot of me and I think the audience doesn't know anything about this brain stimulation stuff, what is before we talk about TMS and kTMP and all these other technologies, external technologies to change the electricity in our brain, what is the normal kind of electrical state in our brain? How does electricity in the brain work? I know this is a really, really basic question here. I don't even know where to start, but basically, how is it even possible that these technologies even do anything to us? If you put this TMS machine up to a rock or a tree or something, it wouldn't do it. But why does it work with the brain? What is it about the brain electrically?
Well, the neurons that are the cell of the brain, they are the one who respond to this electrical input and magnetic input. So when you're able to stimulate them with electricity, then basically you make them fire or more likely to fire. And that's how brain stimulation works, so that you increase the likelihood of the cell of the brain to fire, or you make them fire.
And so tell me about the different brain stimulation technologies that are out there. I know you and Richard Ivory and the people at the Cognition Action Lab have created a new kind of version of this, kTMP, kilohertz transcranial magnetic perturbation. But before that, we have TMS, we have transcranial electric stimulation. I know this is probably a really boring question for you, but just what is the difference between first transcranial electric stimulation and then transcranial magnetic stimulation, and maybe others if those are relevant?
Well, transcranial electrical stimulation is an electric contact method. So you have basically sponges on your head, and there is electricity passing through these sponges, and basically there is the idea that the cortex underneath this area will be stimulated, and this is called sub-threshold method. So you don't really make the neuron fire, but you make them more likely to fire. The problem with tES that is electrical contact method, so there is a safety limitations because you can actually burn the participant with high electricity. But in fact, for safety reason, tES is used at 2 milliampere, maximum 4 milliampere. And that means that the amount of juice that reach the brain is very little and very low. The advantage is that it's continuous method, so you can stimulate for a long period of time. The other one that you were mentioning is called the TMS, this transcranial magnetic stimulation. This is a method that uses a magnetic field to change the cortical excitability. And because you use magnetic fields, you don't have the limitation or the safety boundary of the TES method or the electrical method. The problem with TMS, it's that you cannot stimulate continuously. So you have only pulsed, and the brain doesn't work that way, right? And so what we thought is to invent a method that combines the great features of both electrical and magnetic stimulation that were in the market by developing kTMP, that is a continuous stimulation method, but a higher E field, so higher juice level than the TES. And so we can always reach the brain, basically. And we can do it in a continuous way. And we can also mimic the brain waves. So the hope is that we can change the way that your neurons fire to make them more similar to if there is an imbalance in the brain because you have some disease or there is some something that doesn't work properly, the idea is that we can try to reintroduce the right rhythm at the brain.
Okay, yeah, because I read the paper that you published a couple years ago.
Really?
Yeah, but I tried. I skipped the math part, and well, probably half of it I was like, oh, I don't know. But I was trying to figure out what exactly is going on here. It seemed like there are a couple of different pieces. But now I think I get it. So you're saying there's sort of two sources of stimulation happening at the same time? One is
No.
okay.
It's with the kTMP you're talking about is a magnetic continuous method. So basically, you put a coil on your head, and there is a magnetic field that will go into your cortex and stimulate the cortex. The advantage is that you can do that for continuously. Mm-hmm. So for a long period of time, and you can also decide how to modulate the way that you're stimulated. So you can stimulate at 20 hertz and go to the motor cortex that is the frequency that likes more, or other kind of frequency. The biggest advantage that I think has a kTMP is that there is no sensation for participant. So you put TMS on for instance, on the frontal lobe where they do all the treatment for depression, and you can see that the patient started to have all facial twitching, and the mouth is moving, the eyes is twitching because you have this stimulation also of the superficial muscle, and it's not very pleasant. tES, you can have the electrical stimulation method. The intensity is low, but you can have a itching sensation. When I did it on me, I had the feeling that my hair were pulling out. So it's very unpleasant. Instead, we have tested kTMP now in a lot of participants in higher E field, and they don't feel anything. It's beautiful. You sit there, they get bored, and they're like, okay, something is happening. I don't know what.
Yeah, actually, back when I was an undergrad at Berkeley, I think you were a researcher there at that time. This is probably in 2009 or 2010, I was actually a participant, I believe, in one of the experiments in your lab, because it sounds like that's what happened. I knew this guy, and he must have been working there, and he invited me in. I went in for 3-4 times, and I believe his electrical stimulation, because it's quite uncomfortable. I can feel it. And it's like, I can vividly remember this experience, and there's like a monitor. I'm watching this stuff flashing in my eyes, and this thing's kind of getting my head, like not painful, but like very uncomfortable, and like I'm a little bit worried, like, is it gonna zap me or something? And I never wanted to do it again. I'm like, no more. I'm not so desperate for cash anymore. But so kTMP also, and you're saying with the transcranial magnetic stimulation, it's also usually quite noisy and also uncomfortable?
Well, no, the noise with earplugs, I have to say, TMS, it's fine. You put earplug on and you have the acoustic stimulation. Also with kTMP, you can have some feeling of acoustic stimulation, but also with the earplugs, you don't feel anything. The problem with TMS is, again, that is a pulsed method.
Right.
And so basically you cannot really stimulate continuously, and also you cannot do really stimulate at the frequency that the brain works. So people say, and I'm not a physicist, this is all learning from my CTO, Daniel Shelter. He say, if you think about stimulating at 10 hertz with TMS, you don't really stimulate at 10 hertz because there are so many envelopes. And so at the end, what you really give to the brain is not what really the brain perceived.
I see. So you can kind of keep it going, but you can adjust the level to more mimic the natural brain waves.
Rhythm of the brain. Exactly.
Okay. And it seems like in a lot of these, the ways that TMS and kTMP are being used, it's often used on the primary motor cortex or in the frontal lobes. Why the primary motor cortex? Is it just because it's easy to access? It's right there on the surface, or?
Yeah, it's the way that we basically prove the efficacy of a non-invasive brain stimulation device. Because if you record what happened in your muscles, is a physiological indirect way of testing what happened in your brain. but it's very tangible. You can really measure the amplitude of the muscle activity that is in direct way of what happened in your motor cortex. And so all these methods are being started, TES and TMS, the investigation, the proof of concept have been done through the motor cortex. Once you have that one and you see the change happening in your muscle, meaning in your brain, then we can now, like we are doing now, we can move to different brain area and know that there is something happening in the brain area, there is excitability change in the brain area. And so depending on which brain area you go, then you can have a specific change. Like the language area, you go there, you stimulate, you try to improve, the language learning, or motor cortex because you want to improve behavioral, cerebellar, and other stuff. And the frontal lobe very much the prefrontal because affect the behavior. And so there is all these needs for all the psychiatric disorders that induce change in behavioral, in mood. And so that's the area that the people stimulate is the prefrontal cortex.
Okay, so it's sort of like an industry standard to kind of test it out on the primary motor cortex because that's just the way the researchers do it. And then once you get into the actual, okay, let's do something with this stage, you stimulate different regions of the brain. What excites you most about kTMP? Because there's like a lot of different ways we can apply it, right?
Everything. I mean, so the story is this one. We were there I was there as a scientist, and I was working with TMS.
Yeah.
And then I imported actually tES to UC Berkeley. I was one of the first one to buy the device, and I bought different devices. I remember I started with the one to stimulate your muscle. We modified that to stimulate your head. So very from zero. And I was starting to replicate the experiment that have been done in different lab because I thought that I should learn first. And so I was replicating other study in different labs. And then I got so frustrated because I was not able to replicate results. And then I went to talk with actually the lead scientist of electrical stimulation, that is Michael Nische, wonderful person who really, without any hesitation, helped me to understand everything about electrical stimulation. We collaborate, we work together. But still, I was feeling frustrated by the limitation. And so I went to talk at that point with the physicists. I remember me and Richard Ivory, we were having a journal club about how can we improve the methods. And Daniel, that were part of the journal club, is a physicist and is really like someone who have a deep understanding, I would say, of things. It was like, well, you can't do anything. I'm sorry, this is not possible. You can improve those methods. But I have an idea. I actually have had this idea for a long time, and I was not able to implement it. And so we were like start to talk, and I loved it. And that's why we end up actually, writing a grant in 2 months, got the first 2 awards right away as a innovation idea at UC Berkeley. And then we built the device and we tested, and that's how we started.
You've been studying and doing all this stuff for seems like most of your adult life. I mean, since you were an undergrad, you've been interested in action and how to inhibit action, and I don't know, maybe it's free will or what it is to be a human, how to act. What kind of do you recognize any kind of early signs of interest in this? When did you become going down this path? What were you like when you were a child that maybe led to this, or maybe you just did it for practical reasons? I'm kind of curious, why someone creates something, because you basically helped create this new technology that can monitor and teach us about the brain, but also teach us how to change our actions and change how we think and change how we feel. It's really powerful stuff, and you needed a lot of motivation to do that. So where did that motivation come from?
Well, I'm Italian,
Yeah.
and I studied there all my, undergrads, grads, and I was not very sure at the beginning what to do. And so I have a different path.
Yeah.
But I first started as a therapist, a rehabilitation therapist. And I worked with patients with neurological disorder for 7-10 years. While I was doing that, I was studying psychology. And then I became a neuropsychologist. And so I started to do research again with apraxia. So all people would have a disorder in the motor field, and also language disorders, neglect. So all neuropsychological problem. And then when I moved to UC Berkeley, because I was really wanted to learn more how to be a scientist, then I started to work with this device, and then I put them together. Now all the knowledge of my interest in neuropsychology and clinical that I had in Italy, and my scientific knowledge of UC Berkeley, finally now I am in a stage in which I can put them together. And we actually got awarded, I think 2 weeks ago, from this innovation grant from UCSF and UC Berkeley. It's called the NeuroHub, in which we can use kTMP on stroke patients. So we're going to start actually, I go back to my first interest. I'm going to be able to start and apply kTMP on stroke with the hope that in chronic stroke I can improve the motor behavior.
Yeah, that must be so exciting, because you're going to potentially be able to do and learn so much. What are some of the things that before you thought about the brain, you thought, okay, the brain works this way, but now after doing TMS and helping develop kTMP, you realized like, oh, actually, the brain works a little bit differently than I thought. For example, in depression, people have this serotonin hypothesis, and in mania, bipolar schizophrenia, there's sort of this dopamine hypothesis. They kind of simplify like that. They say it's in the frontal, dorsolateral prefrontal cortex, the left and the right, and all this different stuff out there. I don't know what's true, but what did TMS and kTMP and all this kind of teach you something like, oh my God, I would have never seen that if I didn't do this?
So I think that I'm actually going a little bit backward, because as a scientist, I was very interested in the mechanism and try to understand how the brain works. Now that maybe I'm more wise, I am more interested in how can I change the behavior with my device or my action. And so basically what I'm really interested, again, I have a grant in which I can understand the mechanism in the brain of kTMP, and I'm very interested in that. But what I really want to see is the behavioral change, the mood change. I don't care what happened in the brain as long as it's safe. What I'm really interested is, you cannot grasp that pen or that spoon, and now after kTMP you can do that. That's really for me what I want to see.
Yeah. So one is like helping people who can't, like, say they're paralyzed or they've got Parkinson's or something where they can't really properly move. That's one. What are some of the other ones that are kind of exciting for you? Because right now, like TMS is like largely used on depression, for example. It sounds like that might be the route you're going, but you're more excited about some other things that haven't really been explored yet.
No, I mean, it's my background that made me really go on neurological one, and also our knowledge on the motor cortex. Depression, all these things are not my expertise, but I do see a big potential there, given that we're able to change those brain area. And so actually, I am in collaboration with people that are interested in using kTMP on depression or anxiety disorder, or there is a big field also in substance abuse disorder. So I'm completely open. The other thing that's interesting is the regulatory path in the United States, at least. Neurological disorder, we can actually cannot use a TMS as a predicative, because in the United States it's not being approved by the FDA.
Right.
By FDA approved the treatment of depression for TMS. And so, I'm open to both way. One is more easy on the practical level, and one is more complicated, more interesting. So I'm actually exploring both.
Okay. I'm going to kind of go back and maybe ask another kind of question, but how does How does action work exactly? Okay, so we have the primary cortex, we've got these sort of lower motor neurons, we've got our hands. How do we produce an action? It's a really hard question, but also like, wow, how do we make an action?
Well, it's a balance in a different part of your brain. You plan your action, and then there is a part of your brain that help you to execute the action, and then that part of the brain send the command. I don't know if the right words to the muscles, and so it's a work that start. In different part of the brain until became a more focus on the part of the brain that makes your muscle move.
How can we use TMS to help us learn, not TMS or kTMP, to help us learn for learning or for skill acquisition? Like, how would we do that?
Well, again, there are different brain areas, and each brain areas, I mean, it's part of a circuit, more or less. When I was in early time, you were thinking that there was a specific brain area for a specific, but in reality, it's a circuit. But there are some parts that are more sensitive than the other for a specific cognitive aspect, and so you're going to target that area, and you hopefully are able to change the system, and so improve the learning. Like there is a language comprehension area and a language production area, and so you're going to stimulate, depending on what you want to improve, the production of language or understanding of language.
Yeah. And how about so now you're going to start working on people with strokes, which is pretty exciting. What are some of the possibilities there? I mean, we don't know yet, but what are some potential possibilities in a best case world scenario if it works
for stroke?
Yeah.
So the at least at the beginning, we're going to work with motor behavior. So the idea is to improve their ability and skill in daily behavior. So the independency of the upper limb. That's where we're going to start. So basically stimulating all the area of the brain that will allow you to reach to grasp so that you can perform all the action correctly.
I know some of the other people in the lab there at Berkeley and the lab at Stanford and all these labs there. Some of us are combining it with other things like brain-computer interface, or with virtual reality, or with some of these psychedelics. Does any of that interest you at all, or do you know anything about that stuff?
Yeah. I mean, we are working with. Now we're starting to work with all these new devices in which you put gloves and we can read all the movement of your hands in the space. And we have, also tools that we can record how sensitive we can grasp the object. And then at UC Berkeley, Richard Ivory has actually worked with virtual reality in the last 4 years for a project. And so for sure, I can see down the line as to implementing kTMP with in a virtual space to make it more realistic in the daily life activity.
Yeah. How would we make it? I know it's Richard Ivory's kind of specialty. Maybe you aren't completely focused on that, but how could we use VR how could we use the kTMP or TMS to make VR more realistic?
Well, I always thought as my background as a therapist is you always have to make the rehabilitation related to what the needs of the patient is. So if I can imagine something is you have in this virtual reality environment in which you have actually a coffee and a cup, and you actually create and try to improve in this virtual reality all the movement that you need. And while you're stimulating, and the idea is that while you're stimulating, we can help you being faster and more efficient and more accurate in your movement.
Actually, I've tried one unfortunately another early version of this technology. I was working in this VR company in Tokyo, and some guy came in and had some kind of I don't know what it was. One of these, maybe it was electric stimulation or magnetic stimulation, probably TMS, probably. But we had a VR headset on and had this thing on our head, and it would kind of nudge us to the right or nudge us to the left. Kind of not completely control our bodies, but it would a little bit. I don't remember exactly. It was either moving my hand or it was moving my eyes or moving my neck or something, but it felt strange. I felt like I'm not in control fully.
So I don't know what was it, but
Yeah.
if you put TMS on your motor cortex,
Yeah.
and you stimulate suprathreshold, I'm actually able to make your finger move, make your pinky move so selectively.
Yeah, it was like that.
Yeah, make your arm move. So sometime I also did experiment in which I was putting on the foot area, and so I was able to move your feet instead of your hands. So yeah, you actually can.
But some people might not like this. It's really useful for the people who need to walk. If they need it, like they have a stroke and they're paralyzed. Yeah, I love it because that's the best option. But for people who are fully mobile and everything, they kind of don't like it, right? Or they want their I'm free will.
I don't know. A lot of people want to improve and get better, right? So there are all these companies that are trying to, I remember Halo was putting headphone on, and so you can becoming a better performer in sport, or So there is a lot of people that are interested in cognitive enhancement, I would say, right? Improving and becoming a better learner, better athlete and stuff like that.
That's true. It's like we have bicycles, but now we have electric bicycles or motorcycles, and we can turn our bicycle body into an electrical bike, which I hate. When I see those things driving past me, I'm like, don't hit me. So there'll be these people running super fast or something. Wow. How about can we use it to like I keep asking you the same, like, can we use it for this? Can we use it for that? But has it been used to like, because right now people drink coffee or they take certain unfortunately Adderall or some other things to increase their focus. Has it been used yet to basically just increase focus or that kind of thing?
Yeah, I think there is a lot of study about attention. I'm not an expert on that, but I can see that actually happening, in which you're stimulating part of the brain, in which they can help you to find the target in much faster, and so increase your visual and attention.
So it kind of controls the visual system or the eyes or something like that?
Attention system. How much focused you are in a specific task, or visually or mentally. I don't know exactly the literature there, but I can see that happening.
Yeah, and it seems like there's this chemical side, these chemical kind of research of people, dopamine and serotonin and all that, and then there's this electrical sides. Is there kind of a bridge between them where you do you think in terms of like dopamine and all that stuff, or you're like, no, it's just electricity?
No, but that's because I'm not a doctor, and I actually, for instance, Michael Nisha, that is the tES expert, he's a fantastic doctor, and he can tell you everything about what happened in your brain in terms of neurotransmitter when you stimulate with electrical stimulation. So definitely there are a lot of people interested in that, and there is a lot of people also that do animal models that are really focused on what happened in your brain during stimulation. So a lot of expertise, and I try to learn as much as I can, but again, my focus in the last I would say 4 years is more about how can I change the behavior, and how can I do this one very safely and not a very comfortable way for people.
Yeah. Well, movement is controlled by certain neurochemicals, like, well, one of them will be dopamine, of course, acetylcholine as well. But dopamine is also kind of, if you get too much dopamine, it could be a bit addictive. For example, some of these Parkinson's drugs, people will start getting addicted to things after they now they can move, but now they're also kind of engaging in risky and addictive behaviors. Have you seen any anything like that in any of the studies or anything in your experience where like they can move, but now they're acting a bit too much out of control?
No. And the target of this kind of disease, it's much more subcortical. So right now it's more invasive stimulation that can reach this part of the brain than non-invasive, because there is there is a different deepness that we can achieve with our powerful device. So there are some idea that Daniel has how we can go much more deep in the brain, but that's for next generations.
Yeah, because I was going to ask you about that, because basically these current devices are TMS, and I don't know about kTMP. I wasn't really sure how deep it goes, but usually it's just like on the surface of the cortex, and it doesn't go that deep. It doesn't go into these subcortical regions of the limbic system. Or
that's true. That's true. But the idea you stimulate.
So kTMP is the same.
It's kTMP for now. It is the same.
Yeah.
It's basically cortical stimulation.
Yeah.
Although it's like the other method, the idea is that you act in a system, in a circuit that then reach the subcortical circuits. But again, there are some idea of how can we use kTMP to go and reach deep area in the brain.
But even if you're not reaching there directly, indirectly, you can find this part here, and that kind of links up to here, and in your vagus nerve, and now it's in your heart, and now it's all one body, right? Okay.
That's exactly what we're doing. Actually, we are stimulating, try the brain to start to change some physiological measurement, like a heartbeat.
Yeah. How can you change the heartbeat with the electricity? I know those. What's his name? Nolan. Is it Williams?
Stanford.
Yeah, at Stanford, he talks about this, how by stimulating, I think the dorsolateral prefrontal
DLPFC,
it will like lower the heart rate during the stimulation, and then take it away, and heart rate will go back up.
Yeah.
Is there anything else that you found out there how this changes the heart rate? And is it only in the moment, or can we kind of make long-term changes?
Well, the idea is that there is a plasticity effect, right? So right now, if you do in the moment, you do it in the moment. But the idea is, the hope is that you change the balance in your brain. And so that means that you induce change that are not only in that specific moment, but they can last for longer time.
Yeah. So what do you need to do to increase the odds of it lasting over time? Do you just do more sessions, or is it increasing the intensity, or how do you make the neuroplasticity?
That's so.
It's I think the ultimate question, right?
Yeah, that's you can read paper for years about the dose-dependent effect of non-invasive brain stimulation. It's like I wish it was a very linear effect. It was so simple, but it's very complicated, and so I think it depends really from what device you're using. And right now we are actually investigating those dependent effects, because there are so many parameters that you can change: the duration of stimulation, the interval between stimulation, how high is the intensity of stimulation. And it's probably at the end, my intuition is that there is a spot that is similar for everyone, but then you have to individualize. And I, most of my first years at UC Berkeley was all about how we can individualize stimulation, and because people are so different. I mean, you're talking a lot about the neurotransmitter, and the ticklishing of the brain of people are very different. The scalp thickness is very different. So it has to be individualized, and that's.
It sounds like you're trying to individualize it too with this kTMP. That's sort of one of the beauties of it, is you can individualize it. What's the process of discovering and understanding this individual's brain and skull and system to where you can individualize it? Like, how do you do that?
So one of the things that you can do is recording EEG, and there are specific frequency that your neuron fires, and although there is a range, like you have a alpha or beta, you as a specific person, your power is more at 21 hertz instead of me, it's more at 24. Whoa. And so the idea is inventing, and with kTMP we can actually do that. We can do a closed loop. It's one of the things that we are planning to do, is basically recording what happened in your brain, the frequency of that specific person, and then stimulating back to that specific frequency. That's one of the way that you can individualize, of course.
That's really interesting because you read about, okay, what is beta waves? What are alpha waves? And it gives you this range like 8 to 12 or 4 to 8 or something. And you just assume that, oh, 4 to 8, that's what it is. But then you're saying there's a exact kind of smaller range within each individual. And like, this is your ideal spot. This is what's good for, this is like where you can do this. And in this kind of range of brainwaves, you will do this other kind of behavior or thought pattern or something. And each person has a different kind of range. Whoa.
One of our director of research, Christina Merrick, she's an expert in EEG, and she's the one who is really like focusing on making kTMP closed loop, very, interested in making this circle close.
Now that you've kind of understood a little bit about how the electricity, or a lot about how the electricity in the brain works, and you use these technologies to change it. Kind of strange question, but are there any like kind of natural or other ways for us to suddenly change our electricity in our brain? For example, I'm thinking about our eyes. Like our eyes are sort of, they're our brain, and we see light or we see a firework or something. It's almost like a kind of TMS pulse, that explosion in our eyes, or in sound. If you hear a certain sound like boom, boom, it's music, or it's an explosion or something.
Actually, one of the criticism, or not even criticism, but one of the hypotheses of mechanism of action of tES, right? Because once we discovered that the E field, the power of the electrical stimulation doesn't really reach your brain in a lot of participants because it's not strong enough. One of the theory is that you have this way of changing your brain waves. I'm trying to find the words that are easy to understand, by the frequency of the sensation in your scalp, right? So if you think about it, can be in that way. And the other way is TMS. The pulse can have a sound that has a frequency, and so maybe that is the one who entrain your brain, like the sounds at 10 hertz, the sound at 20 hertz. So there is a lot of way, definitely. But the idea is to understand how strong those waves act on the brain, and how much deeper those change in neurotransmitter and where, so that we can actually induce plasticity.
Yeah, and so regardless of how it works, if say kTMP or TMS, it just produces different results than, I don't know, these bilateral beats or some kind of music or something, then it works. And even if you don't completely understand why, it's kind of fine.
But does that works? I mean, that's the reality. What I'm really fighting about, why I'm here is that yes, works, but doesn't work more than a sham stimulation. Yeah. And so if you want to do that one in a large scale with efficacy for everyone, and that really makes a different impact, you really need to have a consistent, reliable change between people and across time. So that's the main interest, right? Not doing something that works sometime and sometimes doesn't work.
Because even in I know maybe you've done more than 2 studies, but I know you did at least 2, but they got kind of messed up with the pandemic, and some of the participants couldn't complete all the sessions, and there was only, I think, 30 subjects or 29 or something overall. It wasn't a huge study.
Well, we added a third experiment after the pandemic.
Okay.
We have actually now 3 experiments using kTMP. Yeah. And we have 3 experiments using the same parameter, using sham stimulation and real stimulation, and having exactly the same results. It's a pretty good, results. It's a pretty reliable results, having a replication of 3 different studies.
Well, most people don't really have these devices, obviously. Like, they shouldn't probably have them at home. And I guess you can go to the doctor, and for some people who have really serious depression or something and they can't get them, they can use TMS, but most currently, people listening to this are not going to be able to like use any of this. So what are some behavioral tools or nutrition tools? I know it's not your field, other kind of tools that do exist that people could use to kind of change their brainwaves or get some similar results? I know it's a sort of huge question of how do we improve our ability to take voluntary action? How do we sort of increase our increase our free will in a way? Like we can, I can do it. I've taken the action, just like before the machine's making me do it, but now maybe this food I ate or this light, the sun I saw, it kind of helps me get out of bed and move.
Well, on the non-invasive brain stimulation side, there is electrical stimulation that can be used at home, right? So there is one of those techniques that actually you can buy a device and you can use at home. There are also the one who just stimulate your skin, as I was telling you, giving the sensation, and so all these other way that people can use. Again, I don't have direct experience with that, but I know that they don't really reach the brain, and so it's a different mechanism that they can act on some people, but not to everyone. And then, I mean, as a therapist, rehabilitation therapist, for me, it's everything. It's doing and doing and doing and redoing and doing and redoing. Just basically try until the action happen.
Yeah. Well, you have a deep understanding about electromagnetism and all of that. So some people these days are worrying about EMFs and Bluetooth and all that. Should we at all worry about that? Is that going to reach our brain? Is that going to reach our, like these earbuds, for example? Is that going to, the smartphone in our pocket? Is there any evidence that is going to harm us?
I don't have any deep knowledge about that. That's why I have Daniel Sheltra in my team.
No, you're the super genius. You know everything.
No, I don't know. And the good scientist doesn't know everything. That's what the good scientists go to the person who knows stuff. So no, I don't know. I do know that UC Berkeley is a very strict in, of course, safety, and so. Not only we've been evaluated by the committee at UC Berkeley, they also hired an external scientist and evaluate us for the safety of the device. But they also have people coming to test the environment around kTMP, so the room and all the safety related to what you were saying. And we got green light everywhere.
I know you say you want to focus on the practical stuff, but I'm still in this sort of earlier, younger kind of theoretical stuff. I want to understand what is happening in the brain, what is happening. And that's kind of why I made this podcast too. And I've sort of, there's a lot of information out there in terms of like neurochemicals and but this electricity stuff is something a bit new for me. And difficult questions, these all are. But like, what is going on electrically in the brain of someone who or in the spinal cord or whatever, who can't move, they're paralyzed, and what are you changing in the brain that allows them to move?
So my understanding, and again, I have Professor Ganguly, that is an expert in stroke rehabilitation, which I'm collaborating with. So he is the expert and is helping me in understanding how to do that. But the idea is that we're going to go with the perilesional area of the brain. So we are not actually acting on the part of the brain that is damaged, but we're trying to increase the ability of the part near to the brain that is not lesion to take over the part that is lesion. And there is also something during stroke that is the imbalance between the hemisphere that has the stroke and the other one, in which the other one became more active. And so you are trying to reduce this imbalance by stimulating. And so, for instance, you don't have all this spasticity or hyperactivation of part of the body. So it's basically try to restore a balance that has been disrupted by the brain, by the stroke.
Okay. I'm asking you too many hard questions.
No, it's good because the good thing again is the power of a team. And the power of being in an environment like I am, in which I am able to always find the expert in something when I don't have the answer. And that's I think, the power of kTMP and magnetic tides, because we have experts in so many fields.
Yeah, and Magnetic Tides, your company is basically sort of a company that's sort of built out of UC Berkeley, it sounds like.
Yes.
And they're sort of deeply, I mean, the technology was developed at Berkeley, and Magnetic Tides is a company that uses it pretty much. But it is Berkeley pretty much, right?
Well, we spin out, as you were saying.
Yeah, that's what I mean.
Yeah, we spin out, and
Yeah.
actually, in August, a year ago, we won this NIH SBR. That is basically, those are grants that are for companies, so small business like Magnetic Tides, that have innovative ideas that can become a product and go to the market. So I am a spin out of UC Berkeley, and I'm still get a lot of help and advice for all UC Berkeley. And we are working at UC Berkeley because we have a subcontract with UC Berkeley, but we are a separate entity right now.
Of course, yeah. But you still have access to the researchers and resources and stuff.
Yeah, we have a subcontract, meaning that we are using and paying UC Berkeley for doing the research there.
What about bipolar? Because I have a brother who's bipolar, and so I have a little extra interest in this. How do you know anything about bipolar, schizophrenia, and this kind of stuff?
Yeah, so the same is the same idea of the ability with TMS to change not only depression but also bipolar and schizophrenia. There are trials on this kind of psychiatric disorder, and again, we hope with kTMP also to reach that kind of market to help people. The idea is that if you're able to make change in the brain and so to restable the balance, we can, you can start to really investigate if you can help different psychiatric disorder, not only depression. You have to have a target, right? And then the idea, if that works, that you can expand.
I'm happy I can even halfway talk about this stuff. A few days ago, I was worried, like, oh my God, what have I gotten myself into? We're going to talk about brain stimulation. This is really hard stuff. But now you're teaching me a lot of stuff. I'm very thankful for this. So before you mentioned how we can't really get to the subcortical structures, these deeper mammalian, reptilian parts of us. Maybe that's not the language you want to use, but okay. If we could stimulate those regions directly, we can go deeper. What would be the implications of that? What would be possible?
There is a lot of that controlled by the subcortical, right? And so basically it's like, oh, you can actually have surgery and go directly on the heart, right? It's exactly the same thing, but you can do it non-invasively. Can you believe it? It's like that is the goal. You can do all your limbic circuit, like the part of your brain that is related to the emotional, that is very inside. Or you can go DBS now is really surgery because you have to go to the basal ganglia. We can actually go there with the non-invasive brain stimulation. So there is a huge there is an opening of really target specific part of the circuits that are not accessible right now, only superficially accessible.
Okay, so the change would happen probably more quickly, the action and mood and thoughts and traumas or whatever.
Exactly. Yes, because you don't have directly stimulated the brain area that is involved.
How does it's kind of confusing because we have we've broken the brain up into different parts. We say we have this cortex, we've got this limbic system, we've got the brainstem. It seems like what you're doing still though is these parts of the neocortex, the frontal lobes and stuff are communicating still with those subcortical structures. So I want to imagine there's we need analogies almost, but like there's some kind of roads or pathways or doors that kind of connect the two, these sort of pathways. I don't know if you could put words on it, maybe, but what are the sort of pathways how does the neocortex connect with some of these subcortical structures? Are they like, oh, I found a little spot over here. When we stimulate it here, it like really kind of hits the limbic system better. And this place over here, not so much.
Yeah, that's true. There are connections between the part of the brain. And so what I was telling you before, you stimulate the surface of the prefrontal cortex, and you can do change in heartbeat that it's controlled by the subcortical. And so it's like there is a lot of connection. And again, the brain is not it's not the part of the brain are not isolated by each other. It's a system. It's a beautiful system.
Yeah. So what's your kind of ordinary, maybe you don't have an ordinary day, but like what is a kind of brain researcher, brain stimulation researcher, I guess now CEO of Magnetides. What's your day like? What do you do? I can't imagine. It must be like a totally different life.
No, I mean it's a lot of connection now that I'm the CEO, and a lot of understanding stuff that are new, and a lot of also still having the big picture of what needs to be done on the scientific side to making progress that are appealing and also interesting as a scientist, but also appealing for becoming a successful company. Again, we are in 1 year old in terms of funding. So the first
baby,
only 1 year, yes. So, I just came back from RACI, that is a conference in Boston where all the startup, actually NIH invited me, the National Health Institute, where I went to present and pitch in front of investors, the company. And then, yesterday I was at UC Berkeley, like, you do everything, like also teaching the new person how to do TMS because they need some help on the other side, planning all the experiment that needs to be done. But we are a team, but as a startup we do everything also.
Yeah, and you're in a nice location too. Have you used kTMP on yourself?
I did, of course. Yeah,
of course, obviously. Yeah, but okay, like what was it like from your perspective?
Oh, I can't, it's like you don't feel anything. I can't even hear it, but because I'm an old lady.
Nothing.
The 20 years old.
Old.
The 20 years old, they can hear a little bit when they don't have earplugs.
I thought you were 20. You're 20, right? You came out of the womb as a researcher. Yeah. So if you could change something about yourself with now we're getting all personal with say kTMP, what would you want to? What are some things that you would want to change?
I don't think kTMP can make me taller, so I won't say that.
No, I want that one. I need that. That's why I'm in Japan, because I'm too short to live in the USA. No.
So okay. KTMP cannot make me taller, but memory. I will definitely love to have much more memory than I have. I have zero short-term memory.
So how do you keep your memory? Do you just outsource it to Google Docs or something?
Right, everything. Yeah. Everything down. I'm the most organized person you can ever meet, because I write everything, I organize everything.
What's your sort of organization system like? You just have a bunch of doc files or something? Or
one. Actually, I discovered as a CEO that it's a mistake to have a lot of them. I have one doc file, and I write down dates and a person and link to that person, but it's only one document, and so it's like chronological.
But each has a different topic or something, or no?
I mean, one is called external meeting, document. One is called internal meeting, and they are all linked to different other parts.
So keep it really simple.
Yes.
Keep it simple. Yeah. All right. Well, I think it's time to go. Thank you so much for this. And if I go to Berkeley, can I try it? It's not so simple, right?
Call me. 100%. Really? Yeah, of course.
Yeah, I don't know how that works. You can't. It's not like hey.
I can make you try first the TMS and then kTMP.
Give me TES first. Crank it up to get the TES and crank it up to kilohertz. No.
We'll do comparison study with you.
Oh, but one last question. Why exactly? I'm still trying to figure out why the kilohertz, because normally the TMS and these things don't go in the kilohertz range.
Yeah, that's that because it's.
I thought that means it goes deeper, but that doesn't mean it goes deeper. What does it mean?
No, they help you to have a continuous stimulation and a higher E field, because when you with magnetic field, if you increase the frequency, you also increase the intensity. That doesn't happen with electrical stimulation. And so by working on the kilohertz range, we are able to stimulate you at higher E
Okay.
field,
Yeah.
also a higher juice, higher intensity.
Yeah. And then you can kind of adjust it to the individual by 20 hertz up, 50 hertz down, whatever.
Amplitude modulation, yes.
Yeah. Okay.
Exactly.
If people want to learn more about all this stuff, where can they go? I guess it's probably magnetictides.com.
Magnetic tides, yes.
Yeah. Anywhere else? Anything else? Any other resources or books or anything?
Well, UC Berkeley, the Ivory Lab, of course. So that's where we invented kTMP, and then we are starting again now with this NeuroHub Fellowship Award. So that's also going to be on UCSF. That is where you can find information.